Okay, I will just try to do maybe hopefully everyone can hear me. But yeah, today I'll talk about good morning. I'll talk about feature construction for machine learning, new techniques to do it. And a lot of this will be focused on why the motivation, why we should do this. And a little bit I will probably be focusing on the implementation a little bit less than you expect. So yeah, one of the issues that you might observe when trying to apply deep learning algorithms or any kind of algorithm to biology is that they overfit. For example, here's the task of protein ligand binding affinity prediction. You can see that all these algorithms seem to be doing quite well on the training data set, but their error greatly increases when they move out of the training data set. Like you can see this one just sharply increases, makes it no longer the best algorithm, but rather one of the worst ones. So what's the issue here? Issue is that in the biology realm, data sparsity is very significant. The training said that these algorithms only had 5,400 complexes, while there are a lot more proteins in the human body and far more when we consider for the general task of protein ligand binding affinity prediction. So it's easy to fit a model to the sparse data set, but it's maybe not always to the ground truth. For example, you can fit this orange model to this sparse observations that deviates significantly from the ground truth because you are overfitting. The problem, so we had a recipe for disaster. Too many parameters plus too little data is overfitting. It's going to be leading to overfitting. Question is, how do we reduce model complexity while returning accuracy? When we look at the success of deep learning neural networks, we notice that most of the deep neural network is for feature encoding. So, for example, convolutional neural networks are often adapted to a different objective by just retraining the last layer. And shown here are intermediate outputs of a convolutional neural network that are like the neurons are excited about different features. So the proposition that I've that I propose is that an effective feature encoding leads to a simple model that leads to less prone to overfitting. And so that's why I will focus on how do we make this effective feature encoding today. This warrants the sentence, long before modern day machine learning, there was a classifier called algebraic topology, in which we take topological spaces and compute things like topological invariants. These are things like numbers, groups, rings, and polynomials. So we're effectively reducing these spaces under a certain constraint to these simpler representations. So you might have done this you might not know this, but you have done something similar to this while you were a lot younger, probably. You look at those shapes and your teacher might have told you to compute something called the Euler characteristic, which is just the number of vertices minus the number of edges plus the number of faces. Now you can do a little counting on that to get this Euler characteristic of 1, a little counting on this triangle to get an Euler characteristic of 1 as well. But for these three-dimensional shapes rather, you get Euler characteristics of 2. And as a child, when you were younger, you might have deduced that, oh, well, that says that the square is like the triangle, the cube is like the octahedron, but they're not like each other. So that's a topological invariant that you just computed, the Euler characteristic. Now it turns out grown-ups do this as well in something called this homology theory. So colloquially, we're computing k-dimensional wholes, and so a fundamental object here is something called a simplex. These are just generalizations of the triangle. A point is a 0 simplex, 1 simplex, 2 simplex, and 3 simplex. And formally, it's hard to do it in 10 minutes, but this is an invariant that you can compute from the triangulation of a space, and then you generate a vector space by choosing the k-simplices as basis over the reals. And you take this fancy boundary operator, which sends a simplex to each of its edges in an alternating sum. And then you can compute this homology group which is the kernel over image of this boundary operator. And homology is effective at distinguishing different topological spaces. For example, you can see that the one sphere gets different homology groups from the other two, from the hollow two sphere or from the torus. A good thing about homology is that now this thing is independent of triangulation. No matter how you triangulate the space, you will get these numbers. But also you can recompute the Euler characteristic as the alternating sum of homology groups. So parry that, my younger self. And you can also get that the same result that, okay, maybe the hollow cube is like the hollow two-sphere. That's good. One of the ideas of how do we bring in extra information now? Because topological invariant is invariant under topological deformations, but we want to encode something like the geometry of the space. So we introduced something called the filtration parameter, in which we build up a sequence of topological spaces and progressively compute the homological invariance from it. So we can, and that gets us you see here, there's a hole, here the hole disappears, so there's a bump in the middle. And that idea is called the persistent homology. So that brings me to my undergraduate work, which was an algorithm called predicting affinity through homology, which takes a protein ligand complex and uses persistent homology to encode and do after some feature selection, encode a 10-dimensional vector, which is then fit through a very sparse set of regression trees, 13 regression trees. That's nothing compared to modern day machine learning algorithms to get the binding affinity. And so my algorithm is generalizable in the sense that we don't overfit compared to other algorithms. It's interpretable because the homology is good and we can figure out which atoms contributed how much to the prediction. And finally, it's fast compared to previous implementations due to a design in here. So this shows the simplicity and representational power of homology. But now here's the question: how can we directly encode the geometry rather than using this filtration of simplicial complexes? The idea is to introduce something called the differential forms. Actually, this is just forms of a function and followed by this little sequence of called infinitesimals. And you've used differential forms in calculus, you just didn't know it. Also, we didn't write this funny wedge product in there. So that's just the integral. It's just the integrand of whatever you put in calculus. There's the idea of a differential, which is the idea of a total derivative generalized to differential forms, where you take the sum of partial derivatives followed by by a little thing to remember where you take the partial derivative from. And now you can introduce maybe your favorite theorem from calculus called Stokes' theorem, which just phrases that if you can the boundary, you can take the differential form over the boundary of a manifold, and that will be equal to the differential over the entire manifold. And finally, the operator that will be of crucial importance to us today will be a Laplace-de Rham operator, which takes a K-form and returns a K-form. This generalizes the Laplacian that you might remember from multivariable calculus, that is the sum of all partial double derivatives. To generalize this operator, you need to define something called the Hodge-Star operator, which takes the K-form to an n minus K-form on an n-dimensional manifold. And then the Laplace-de Rham operator is just this chain of differential and Hodge-Star operator. I'll show you one of the most significant theorems in early 20th century mathematics that says that for an n-dimensional manifold M, the simplicial homology that I briefly talked about before is isomorphic to this space of harmonic forms, which is the set of differential forms which under the Laplace operator amounts to zero. Now, this is really something surprising because now we're saying something about differential. We're saying something about we're saying that the behavior of differential forms captures the topology of the space and some geometry, as we will see. So the idea of these two papers is to analyze this Laplace-de Rham operator on biomolecular structures and phrase it in some way as manifolds embedded in R3. So some abstract nonsense, the delta as the operator is on bounded sets of Rn is linear and self-adjoint, which follows from calculus. It has finite dimensional kernel, which follows from the isomorphism that we just talked about. And so it turns out that we can analyze its eigenvalues because its eigenvalues are real and discrete. The eigenvalues are called the spectrum, and that will be of central importance in our paper. So the question is, like, how much geometric information is encoded in this spectrum of this operator? And that is popularized by this 1963 paper by Mark Katz of Rockefeller University. And the idea is that the shape of a drum determines the set of frequencies that it can generate as its eigenvalues of a boundary problem. And the question is, how does knowledge of these frequencies give back the shape of the drum? So in 1911, Hermann Weyl said that the volume can be determined by the limiting behavior of these eigenvalues given by this formula. In 1992, three people said, okay, actually, no, these two drums generate the same frequency. But when you look at them, you're like, those don't look like drums. They're kind of weird shapes. And it turns out in 2009, somebody figured out that, in fact, if you give out certain good constraints about like the shape of the drum, the shape is round, the shape is symmetric to a certain extent, then the spectrum of delta will uniquely determine the shape of the drum. So the moral of the story is that the spectrum of the Laplace-de-Rham operator tells us something about the geometry of the underlying object. Now, okay, now this is data structures class, so we got to talk about the implementation. The idea is that how do we implement the operator delta given a triangular mesh of, say, a biomolecule? There are only these two operators in here. If we can implement these two operators, it'll be good. I'll just talk about implementing the D operator, the differential operator. So for a differential form, the idea is to store it as using the integration map as its integral over each of the simplices in our triangulation. And so that's a vector. And now we have the D map, the differential map on the differential form side. And we want to find a map D hat under the discrete differential form side that behaves such that this diagram commutes. Now, actually, but it turns out by Stokes' theorem, if this d omega, the definition of d omega will allow us to push this differential as a boundary down here. And so this is actually, this d omega hat is just the alternating sum of omega hat. So D is just a matrix related to how the boundary relates to all the lower dimensional simplices. And star can be implemented similarly. So stack delta is just a matrix eigenvalue problem. Okay, so the two papers that I put on are just the ideas of, okay, maybe how we can analyze delta in biomolecules for a better flexibility analysis, better electrostatics analysis, or maybe adding the evolution to the manifold perhaps captures more information. I mean, this is a minuscule improvement than the other previous algorithms, but these authors tend to be not very good at doing biology related stuff. Okay, so that's the end of the presentation. Thanks.